We're looking at chapter 5 and we are on page 66. We're going to start this off by looking at different kinds of functions, exponential functions, and how they grow and how they decay. Linear functions look like a line, right? They have a degree of 1. Usually when you see a linear function, it looks like this. And these are all numbers, but the variable has a 1, so that's why it's a first degree. Quadratic functions look like a smile or a frown. We call these curves that are concave up or concave down. And it has a degree of 2. So quadratic functions usually take on the appearance of ax squared plus bx plus c, second degree polynomial. Exponential functions look like, how do you explain this? I'm just going to draw it. They start off flat and then they raise up really quickly, or they come down really quickly and become flat. And exponential functions look like this, where we have x in the exponential spot. The way that we usually see exponential functions is in this form, a times b raised to the power of x. So we're going to look at that a little bit more. What I like to do is I like to give a name for a. A I'm going to call, and this is going to work in a lot of scenarios, the starting population. And then b is what we're going to call the multiplier. And you'll notice that b can be a number that is greater than 0, but it can't be 1. If it's 1, then this wouldn't be exponential. So b can be a number that is greater than 0, but it just can't be 1. One of the questions I always like to put out there whenever we're talking about exponentials is, I want you to imagine that there's a lottery and that you win this lottery. It's a state lottery. And you can have one of two choices. One choice is that you get $1,000 every day for 30 days. And then the other choice is that on the first day, you get a cent, 1 penny, but then for 30 days, you get double what you got the day before. Which one would you pick? Most people do the math right away and know that this is going to be $30,000. Seems pretty good. The 1 penny kind of doesn't seem as attractive, but let's take a look at and analyze this really quickly. So I'm going to actually put a blank on here. And I'm going to look at this penny a day a little further. So you know that we have roughly 30 days in a month. I'm just going to put the first 10 days as the first column. Here's the next 20 days. The next 10 days is 20 days. How much of an impact would it make if my month had 31 days as opposed to 30, and is that really a big deal? The first day we get 1 cent. The second day we get 2 cents. So now, just so you know, we have in our pocket 3 cents, right? Because, yeah, 4 cents, 8 cents, 16 cents, 32 cents, 64 cents, $1.28, $2.56. These are what we're getting every day. So if I'm looking at this, I'm thinking I may have somewhere around $4 some odd cents after 10 days, right? Then we keep going. We have $5.12, $10.24, $20.48, $40.96. This is where it starts to get wicked fun. $80, $81, and some blah, blah, blah. I'm going to show you a table. How about that? I'll make a table. You don't want me to do this. I don't want to keep looking these up, so stay right there. Okay, so here's my little picture from the table. One thing I realized was I'm like, oh, my 13 was not that. When I was back here doing the numbers for the first row, I skipped 9. So that's fun. At least that was kind of fixed in my picture. So here you can see after 20 days, the amount of money I got on the 20th day was $10,000, which you can add to the 5,000, get 15. Here's 16, 17, 18,000. Okay, so we're at 20 days and we're almost at 20 grand, maybe 18, 19 grand. I'm just putting this in my head, maybe a little less than that. Okay, so that's pretty cool. What happens if we put another 10 days in? So let's get my next picture. So here's the next 10 days. Notice that on the 21st day alone, you got $21,000. So now you're well past the 30,000. Add another 40, 70,000. Add another 80, now you got 150,000. Notice on the 24th day, you more than doubled that, right? $167,000 on the 24th day. That added to all of the ones before. I mean, we're well past like 300,000, and then you add another 300,000. You keep adding, and then the numbers get so big they have to use scientific notation. On the 30th day, 1, 2, 3, 4, 5, 6, 7. Put a 0 there. On the 30th day, you get $10 million alone. Remember when I was saying, does it matter if there's 31 days in a month? Well, yes, it kind of does, because on that 30th day, if you had one more day of doubling, that one day alone would be worth 21,474,484. So kind of important. That penny a day being doubled every day for a month grows exponentially, which is pretty cool. So what I want to do is I want to start to look at exponential functions and try to grasp the power of what an exponential function does when it grows or it decays. So we're looking at this example. 7 people start off having knowledge of a rumor. Every hour, the number of people that know of the rumor will triple. The function looks like this. So this is hours right here. And this is going to be people that know the rumor. At 0 hours, 7 people know, right when we start. After the first hour, we have to triple, so now we have 21 people know. The second hour, it triples again, so now we have 63 people that know. The third hour, it triples again, so now we have 189. And then after the fourth hour, and so on and so forth, you can see how it becomes. Remember that whenever we write the equation for an exponential function, A represents the starting population and B represents the multiplier. In this case, the starting population was 7, and my multiplier is tripling, so I put a 3 in here, raised to the power of x. This is how I develop the exponential function that represents this relationship. It's actually quite simple. Let's do another example. You have to be thankful I didn't use any COVID examples because I'm all COVIDed out. The bacteria E. coli will quadruple every hour if there exists a starting amount of 7 bacterium. A, write an equation to represent how much E. coli exists at any given time. X is going to be equal to hours. Again, remember that Y equals A times B raised to the power of X. A is the starting population. In this case, that's 7. B is the multiplier. Quadruple means 4. Raised to the power of X. X represents hours. So every time X goes up by 1, 2, 3, every time it does, it will grow by 4 times. How many bacterium exist after 24 hours? This would go on my calculator, because I'm not going to do this in my head. I'll grab that off of Desmos. Here it is off of Desmos. Again, it's a big number. It's so big they have to use scientific notation to express it. If I wrote that out as standard notation, it would look like 1. Okay. Goodness. I couldn't even write it all in one line. It's a big, big, big number. Something quadrupling every hour grows extremely fast, as you can see. The graph to the right represents exponential growth. If I look at this from left to right, it's growing. Whenever the multiplier is a number that's greater than 1, then the function is going to grow. And so this is what a function looks like when it grows, and the exponential function that's going to represent that is going to have a number that's plugged into here. This number is going to be bigger than 1. So let's talk a little bit about exponential decay. This is a little bit different. Again, we are going to be talking about the starting population, the multiplier. Notice that for decay, it's a number that happens between 0 and 1. It can't be 0, it can't be 1, it can be bigger than 1 because we're talking about decay. So it's going to be like 1/2 or 1/3 or 1/8 or 0.215 or whatever it is that you have that could be the multiplier, but it's going to be a number between 0 and 1. And then we have on the top of our exponential x over a term of time. And I'll explain this in just a moment. A bacteria has a half-life of 10 years. If there are 800 bacterium at the start, then f of x is going to be 800. Half-life means that my multiplier is 1/2 or 0.5. And then the time is going to be x over 10. So x represents years. And since this has a half-life of 10 years, it means that it would take 10 years before a full half-life happens. And so if I had 10 years, I'd plug in 10 for x, and that would be 10 over 10, which is 1, which means it went through 1 half-life. If there was 20 years and it was 20 over 10, then that would be like we went through 2 half-lives, right? Because they happen every 10 years. So that's why we have to make our exponential spot a fraction. So let's look at this together really quickly. Again, this is going to be years, and this is going to be number of bacteria. We start off with 800 at 0 years. 1 half-life happens after 10 years. So, oops, hold on a minute here. I just put these in here backwards. Nothing like a little dyslexia. Okay, 0 years, 800 bacteria. After 10 years, there's going to be 400. 20 years is going to be 200. 30 years is going to be 100. Notice that I'm picking my years to fit my problem to make my life easier. 40 years means I'm going to have 50. Notice I'm going to get closer and closer and closer to 0. I'm actually never going to quite reach 0 at the rate I'm going, but I will get to a very, very, very small number. What happens when we are graphing something like this? So imagine this is 0 years right here. So at 0 years, I have 800 bacteria. Then here's 10 years. This will be 20 years. And this will be 30 years. And this will be 40 years. And every time I go up by 10 years, my distance to 0 is cut in half. You can kind of see that exponential decay happens at a very fast rate. So this is from left to right. You can see it goes downhill. That means that this is decay. How much bacteria is left after 3 years? Okay, that's going to be not a pretty number probably. So I'm going to use 800 times my multiplier raised to the power of 3 out of 10 years. this is going to be a problem for Desmos. So here's my answer from Desmos. 800 times 0.5 raised to the power of 3 out of 10 years. You would have 649.8 bacteria after 3 years. It's a number that's smaller than 800, but it's not a complete half-life, so this makes perfect sense. Let's look at the next example, which is going to be in the next video.